Well, hello everyone, and thanks for joining us today. This webinar is the final presentation in the series called Missed Opportunities. And if you haven't seen our other two yet, I would highly encourage you to watch them. Our first was on smart manufacturing, and our last was on cybersecurity. And all of them have been recorded and posted on our website. Following suit to the previous two, my presentation today will be about missed opportunities related to machine safety when trying to improve both safety and productivity. If you have questions throughout this webinar, please enter them into the chat window and our marketing team will forward them over to me. And if we happen to run out of time at the end, don't get to your questions, you can always follow up with us. So that being said, let's get started. So my name is Jeff Winter and I lead Grantek safety practice. And as part of this position, I'm pretty active in the industry, really so that I can give the best possible insight to our customers. Not only do I want to be credible when it gets down to the technical stuff, but I also want to be able to look holistically at the bigger picture, having a pulse on industry struggles, industry trends, and even technological advancements. And all that experience kind of weighs into this presentation that I'm going to give today. But to understand why the safety practice even exists, it's helpful to have an understanding on how Grantek goes to market. Currently, we have 3 strategic initiative groups: smart manufacturing, safety, and IT, OT, and cybersecurity. Each of these groups are the key areas of focus that align with Grantek's strategy of being a turnkey provider as we embrace the Industrial Revolution 4.0. Each group is tasked with being thought leaders in their respective areas, continually looking forward in the industry, innovating new and best-in-class services that really maximize the benefits of some of the technological advancements out there for our customers. So in short, we don't dabble on these topics. We aim to be leaders so that we can help guide the industry with our insight. And I think that's a perfect segue to our presentation today, which is missed opportunities in machine safety. So none of the items I will cover today are about things that you might currently be doing wrong or that could lead to safety projects failing, but rather things that you probably aren't fully taking advantage of, hence missed opportunities. If considered at the right times and implemented where appropriate, taking advantage of these opportunities will inevitably increase your overall productivity and hopefully lower your operational maintenance costs. And all this is still in addition to the obvious goal of making a safer place of employment. So the missed opportunities that I see most often, and this is both in small and large companies, are not separating protective stops and emergency stops, not including control of hazardous energy in your safeguarding risk assessment process, not upgrading your safety when upgrading machine controls, not taking advantage of integrated safety, and not including safety in your connected enterprise or MES strategy. I tried to structure these so that we start more technical and work our way up to bigger picture ideas. So we'll start off with the most technical, diving into the weeds of safety circuit design. I want to talk about the missed opportunity of not separating out your emergency stops and your protective stops. So let's start with definitions. An emergency stop's purpose is to remove power from all elements of the machine that cause motion or harm. And this can either be done by immediately removing power, like unplugging the machine from a wall, or doing a controlled stop and then removing power. But no matter what, an emergency stop has to remove power. A protective stop, on the other hand, though, has an entirely different purpose. Its purpose is to put the machine in a safe state, which doesn't necessarily mean you have to remove power. And that's where the missed opportunity is. Most companies, and really most engineers, remove power for both their emergency stop devices and their safeguarding devices. Now, is this allowed? Is it okay? Well, sure. As long as your emergency stop removes power and your safeguarding device put the machine in a safe state, which we will assume that removing power accomplishes a safe state, then absolutely you can combine them. There's nothing wrong with this method. In fact, we probably see it over 60% of the time. It just misses out on other possibilities. So let's look at a typical system. You have your emergency stops all wired together into a safety monitoring relay that goes into a set of redundant contactors that removes all power from the actuators. Simple circuit. You push the e-stop, power is removed. That's it. But nearly every machine also has some sort of safeguarding device as part of it. In this case, we'll assume a couple interlocks and a light curtain. What do most engineers do? Well, they run those safeguarding devices right into the same relay, executing the same emergency stop function. So if you hit the e-stop or trip any safety device, the same end result occurs. Power is removed everywhere. Once again, is this wrong? No, it's just probably not optimized. So now let's separate out the functions. An emergency stop function and a protective stop function. Visually here, I chose to replace the safety relay with a safety PLC for simplicity, but this can be done with just a couple of safety relays. Now in this scenario, if you hit the e-stop, power is removed. That's the same as the last setup. However, now your safeguarding devices, the interlocks and the light curtains, execute a protective stop command instead of executing the same emergency stop command and removing power. When they're separated, now you have a lot of options available for what your safeguarding devices actually do when they're tripped. Think about just pausing the machine as an example. No power removed, just a safe stopped position. To the operator, this would look and feel like an emergency stop, but under the hood, all the power's still on. The safety system ensures prevention of unexpected startup. Now, how would that help productivity as compared to removing power? Would startup times be faster? What if we took it one step further and we take advantage of safe motion technologies, which can do a bunch of things instead of just removing power or even pausing the machine? Safe motion technologies today follow IEC 61800-5-2, which spells out how to do over a dozen or so different safe motion capabilities. For example, safe operating speed, safe acceleration, safe torque, safe direction, safe range, you name it. So now imagine instead of just pausing the machine when a safeguard is tripped, you slow it down to a safe speed, say 10% of operating speed. How much better is that than removing power? Hopefully you can use your imagination here to see the possibilities and ultimately the value. Now you might be thinking, why isn't this done more often? Why isn't everyone doing this today? Well, the biggest reason I think is because most people think all safeguards have to remove power, like emergency stops. So they just lump everything into one big simple circuit. That thought process, coupled with a limited knowledge of safety technology, it limits productivity enhancing options like this. Is it wrong? No, but it sure misses out. The technology's there, the industry safety standards support them. It's now on you to take advantage of them when and where they can benefit you the most. So the takeaway here is really when considering safeguarding solutions, don't limit yourself to thinking you always need to remove power like emergency stops. If your current safeguarding system is causing long restart times on equipment or just having some sort of negative impact on production, this absolutely should be worth looking into. The ROI could potentially have huge paybacks. Now let's take a look at our second missed opportunity, not including control of hazardous energy in your safeguarding risk assessment process. Now the concept of control of hazardous energy, which most people think of as lockout tagout, versus the concept of safeguarding is probably the single biggest topic I educate customers and the industry on. The image here represents the common battles I see happening all over the industry. On one side, you have eh&s that thinks lockout tagout's the only way to keep people safe and demonstrate compliance with OSHA regulations. And on the other side, you have operations constantly complaining about how lockout tagout is hindering production. Does this sound like a situation you might be in? Unfortunately, as a result, it means a lot of companies lock out more than they really need to. So what can we do better? Well, to start, we need to understand where lockout tagout and machine safeguarding intersect. If you have a particular machine you're looking to make safe, you'll need to apply both lockout tagout and machine safeguarding. They serve different purposes, which is why they have different regulatory requirements, yet they both are essential to providing a safe machine. Lockout tagout applies only to service and maintenance tasks, where the default go-to requirement is to lock out the machine by removing hazardous energy. Machine safeguarding applies to general use and normal production operations. A good visual might be to think of it as child-proofing the machine, where the go-to requirement here is to keep people away from the hazards through physical guarding or by adding safeguarding devices that either detect people entering an area they shouldn't be entering or detecting people inside an area that they shouldn't be inside. In both cases, these devices must ensure that the machine enters a safe state. But that safe state doesn't necessarily mean locked out, and that's part of the confusion. As you hopefully are able to figure out, the main distinction between the two is based off the particular task at hand. Depending on what the employee is doing determines the type of protection that's required or should be used. You can think of it like this. If an employee needs to do something to or with the machine, the default is probably locking out. But if a curious employee walks up to the machine and says, "Ooh, what's that?" and goes to try and touch it and they can get hurt, that's where you really need safeguarding. There's a lot of obvious tasks where lockout tagout can make sense, such as replacing a motor, but then there's a lot of other ones that don't fit too nicely into the requirements. And this is where we enter the elusive space called the minor servicing exception. This term, minor servicing exception, it's actually just an industry way of describing a small note in 1910 147 A2II. This one little note, which I'll read to you, is what gives employers the ability to not apply the requirements of lockout tagout. It's extremely powerful, even though it's so short. It's one sentence. So I'm going to read it to you. Minor tool changes and adjustments and other minor servicing activities which take place during normal production operations are not covered by this standard if they are routine, repetitive, and integral to the use of the equipment for production, provided that the work is performed using alternative measures which provide effective protection. Now, first pass, that note may seem to make perfect sense and easy to apply. But this minor servicing exception has been one of the most controversial aspects of machine safety for many years. The devil's in the details. Defining what each of those underlying items mean and how they are determined can make or break your ability to claim this exception. Essentially, this exception allows employers an ability to use their general machine safeguarding, assuming it's adequate, as an alternative to lockout tagout for special set of tasks. Now, every company has a control of hazardous energy program, which mainly lays out the requirements for locking out and tagging out. Some may be better than others, but everyone has one. It's a requirement. Not nearly as many companies have a machine safeguarding program, which defines how you properly safeguard equipment, because that program isn't a requirement. And only the best in class usually have their control of hazardous energy program nicely link up with their machine safeguarding program to take advantage of this minor servicing exception, which, related to our topic here, is the missed opportunity. If you keep these programs entirely separate and don't fully take advantage of the minor servicing exception, you will undoubtedly over lockout. So how can you take these two concepts and make them work together? It all starts with the risk assessment. On the left here, I have a basic workflow of the risk assessment process as defined by ANSI V11.0, the most commonly used in the United States, which is harmonized with CSA Z432 in Canada and ISO 12100 in Europe. Most companies I work with understand this process for assessing and reducing risk. However, most companies narrowly apply it to just safeguarding. They have a separate evaluation for their lockout tagout program. So my question is, why have two? Because if you combine them into one and you do it correctly, you can really open up new possibilities for improving safety during certain minor servicing tasks, as well as limit the number of times of locking out. The first step you really need to do is to ensure that your risk assessment process is task-based, not just hazard-based. Although both are allowed and effective in providing adequate safeguarding for normal production, only task-based really can know the true risks when someone is getting inside a machine to fix or repair or maintain or really do anything that requires intervention. The first rule that most people overlook with locking out, though, is if you can demonstrate there is no hazardous energy or no hazard, then you don't need to lock out. But the only way to do that is to evaluate the risk of each task. The next part of the process is to evaluate each remaining task to see if they qualify for the minor servicing exception. A simple checklist like the one I have on the screen here, which uses the requirements of OSHA 1910-147 and ANSI ASSE Z244.1, the industry standard for control of hazardous energy. It can help you determine if a particular task in question is even allowed to claim the minor servicing exception. So at this point, you would know which tasks require locking out and which ones could rely on safeguarding. Now, it's very important to note here that this step is just a qualification step, which is why I put the emphasis on could, because it doesn't really mean that your safeguarding provides effective protection. It just means that a particular task can rely on safeguarding. You will still need to verify the safeguarding design, you'll need to validate its installation, and ensure the residual risk is acceptable before you can use it. A holistic risk assessment that includes control of hazardous energy is a very common missed opportunity. It's only a small adder of time to do this as part of your safeguarding risk assessment, yet can save you lots of time in the long run. It also gives you a better opportunity for replacing some traditional tasks that require lockout with newer technology at the same time that you're updating or upgrading your safeguarding. Now, some of you, once again, may be thinking like, oh, come on, Jeff, you're telling me most people don't already do this? Yes, that's exactly what I'm saying. If you look at the roughly 700 or so risk assessments Grantek's performed for customers, maybe only 50 to 100 times we've been requested to evaluate safeguarding and control of hazardous energy. What's that, 10% at most? So next time you think about doing a risk assessment to evaluate your safeguarding, you should probably consider including your control of hazardous energy as part of it. All right, let's keep cooking here. So missed opportunity 3, and this is my personal favorite, not upgrading your safety when you upgrade machine controls. This could also be phrased not upgrading your machine controls when upgrading your safety. It's interchangeable. The fact is, financially speaking alone, you absolutely should consider safety when doing controls, and you absolutely should consider controls when doing safety. So why is this one my favorite? I like this one because I think most people anecdotally would agree that this makes sense in theory, but there's just no data to back it up. Well, that was until Control Engineering Magazine actually asked me to put together a case study to answer this exact question. Does combining your automation and safety upgrades save you money? And after doing the due diligence and research, the answer was a resounding yes. So as we go through all these cost savings considerations, you may be thinking, this is silly. We always combine these types of projects. No one separates them like you have presented that. Well, let's use Grantek as one of the examples. Again, a company who has upgraded the safety on hundreds of machines and upgrade controls on, oh gosh, thousands of machines in just the past few years. How many times have our customers combined their automation and their safety projects? Probably only around 20-ish or so times, which is only about 5% of the safety projects. That's not a lot. So no, most of our customers are still separating their projects. The biggest reason I'm guessing is that they aren't even considering the financial impacts of not combining them because they view the projects as so totally different. And that is what we're here to talk about today. So our case study here is a real-world example, and unfortunately all too common in the industry. A customer comes up to us looking to upgrade a machine, and in this case, 2 depalletizers to make them safe. The impetus behind this upgrade, an incident. Make it safe and make it safe now. The second project was an upgrade to the obsolete PLCs on the same depalletizers and just add some HMIs. The request for this was about 6 months later. Although it was the same project manager asking for these 2 projects, they were funded from different buckets. So let's dive into the details of the first project. These are the typical areas we break out our costs for projects, the major categories. The safety project included upgrading the guarding, adding safety devices, upgrading the safety control system, which, because they had no space in the control panel, required a secondary panel. It's fairly standard here. You can see your mechanical hardware, your electrical hardware, and installation. They take up a bulk of the price, and upgrading these 2 machines, in this example, a little over $200,000. We got the order right away, and we upgraded it. Now let's look at the pricing breakdown of Project 2, which remember was requested 6 months later, after we already upgraded the safety. So this project including replacing the old Modicon PLCs with Allen Bradley control logics and adding panel view HMIs. Complete PLC migrations and adding modernized HMIs, if you've never done it, it can be expensive. I mean, the cost of this upgrade was just shy of $100,000. And because of the cost, the customer chose not to do this upgrade. It was too expensive. They'll just wait it out. Now, in hindsight, had we had this case study at the time, I'm sure we could have changed their mind, but we didn't. So here's a visual of the 2 projects from a controls perspective. Project 1 had a bunch of safety devices going into a safety controller, which had basic communication with their existing Modicon PLC. Project 2, had they chosen to do it, would have been to convert the Modicon PLC to a control logics with the addition of an HMI. So those were the 2 completely independent projects. Very typical, once again. Like I said before, more than 95% of our projects just look like what you saw. One project to upgrade safety, another to upgrade controls. Adding the project costs together is just over $300,000. In this first case study, we're going to talk about the potential savings just by doing the projects at the same time. That's it. No changes in scope, no changes in hardware, no changes in functionality, the exact same solution, just do them at the same time. So how did we come up with these values? Well, we created real quotes for the independent projects per the customer request. All we did is we just went back and we developed a new quote, assuming that we were asked to do the project simultaneously. Now, as you can see here, there's a total savings of around $46,000. It's about 15% of the cost of both projects. However, it's nearly half of the cost of the PLC project by itself. Just by combining them, they would have got half the PLC project paid for. Let's look at how we calculated some of these numbers. Knowing the solution didn't change, there's zero changes to mechanical design and mechanical hardware and electrical hardware. There are, however, noticeable changes in project management, system integration, electrical design, commissioning and startup, even a tiny bit in installation. Why did some of these numbers drop so much? Well, the biggest area dollar-wise is electrical design. We had to modify 12 of 15 existing drawings and create 14 new ones for the safety project. And if we redid the PLC, we would have had to redo all the 15 of the drawings and add a few new ones. Other areas of savings include less project management time. You only have one planning schedule, one set of kickoff meetings and reviews. There's also a good chunk of time saved in system integration through limiting the number of times code needs to be rewritten, and in your commissioning time for conducting SATs and debugging install. So once again, just by doing the projects at the same time, changing no part of the scopes, could have gotten half the second project paid for. So I just showed how you could save around $46,000 just by doing the projects at the same time. Now I want to take it one step further. If we did both the projects at the same time, a few engineering possibilities open up. Now I won't talk about the cool changes in functionality you could get. Let's say, for example, like monitored entry exit into the Depalletizer cell, or advanced safety data reporting, or zone control. None of that. I'm not going to talk about any of that. I'm only going to talk about the savings associated with simplified design and how that relates to overall project costs. But keep in mind, if we were truly doing both projects simultaneously, we would absolutely suggest entirely new solutions that can take advantage of some of those more advanced safety systems. I mean, why wouldn't we? It's already built in, and now's the time to create the new functionality. But if I can show you the benefits without taking advantage of any of those cool new features, imagine the story that can be told if we do. So if we re-engineer the solution, we'd have no reason for a dedicated safety controller and therefore a second control panel. We would just combine all the controls, the machine controls and safety controls, into a single safety PLC. This simplifies the design dramatically. We'll keep the costs from the previous case study here so you can see the compounded benefits as we expand them. On the left is the total from before, 303 grand. The next column showing how just combining them saves you around 46,000. And now we're going to add the re-engineered column, which shows an additional cost savings of simplifying the design. The savings in bold will show the combined total savings, and the saving increases in red show the added savings from the re-engineered solution. So overall, you can see that there's an additional 14,000-ish in savings with simplifying the design, taking the total to around 60,000, or what would happen to be around 60% of the original PLC upgrade project cost. We aren't changing the mechanical design or hardware, the mechanical hardware, and we therefore can assume the project management's the same in this case. So let's look at a few areas of additional savings. There is some savings in programming through no longer needing to do handshaking. Electrical design is reduced due to needing about 10 or so less drawings. And the potentially most surprising one is the small savings in electrical hardware. Now, a safety PLC by itself does indeed cost a little bit more than a regular PLC, but by having the safety PLC, we eliminate the need for a second panel and all its associated hardware, so it actually adds a small bump in savings. So overall, found 60,000 savings, not a single change in functionality. How much else do you think could be saved if we actually did change the functionality and took advantage of the built-in features of, let's say, the safety PLC? Or, for example, we also upgraded things like servos or a pneumatic system. Hopefully you can see here how doing projects at the same time can really reduce overall costs. So some questions you may want to ask yourself is, does my company have any planned safeguarding upgrade projects in the next 5 years? Or does my company have any automation related upgrades in the next 5 years, especially anything that relates to obsolescence planning? So let's take it one step further again. Instead of looking at just the direct cost for the projects, what if we look at downtime as a result of projects? Now, downtime doesn't change the cost of the project, but it sure can hit the bottom line. So we don't know the amount each day or each hour of downtime cost you, but I'm sure that you or someone in your company does know the answer to that. So you would easily be able to figure out how much this downtime translates into real money lost. So the average number of production downtime days is about 6 for a safety project like the one we just showed earlier. Coming back at a later date to do a PLC upgrade might take up to an additional 4 days of downtime, totaling around 10. Combining the projects here saves you between 2 and 3 days of downtime. So how much money does that save your company? Heck, I'm guessing that 2 or 3 days of downtime could potentially be more expensive than the whole PLC upgrade project in its entirety. This reduction in downtime could alone just justify combining the projects. You may not have considered that. Like I mentioned in the beginning, this case study was published in Control Engineering, so if you want to learn more, we can guide you as to where you can download that article. All right, missed opportunity 4, not taking advantage of integrated safety. Now, this missed opportunity is the one that probably has the most buzz already in the marketplace. I mean, most people generally are already aware of this because hardware manufacturers like Rockwell, Siemens, Omron, Bosch, you name it, they do a good job of advertising the benefits. So instead of regurgitating what they have already said, I want to share a different spin on the same idea. So let's remind everyone the concept of what integrated safety is. Well, integrated safety, as its name would imply, means that the safety features and even safety components are integrated into machine and motion control systems. So instead of having a set of hardware that makes your machine run and a separate set of hardware that makes your machine safe, which up until a few years ago was the norm, now the devices are being consolidated together, integrating the functionality. So as technology has advanced, control manufacturers have realized it's actually just less expensive to make safety an option built into their regular automation components as opposed to having a whole separate device or a whole separate line of devices. So now you have safety being built into your logic devices, built into your motion control, built into your fluid power, and even built into some of your detection systems. From a hardware perspective, this is great. Less hardware means less cost, less spare parts, even smaller control panels. Most new machines are being built with hardware that has safety as an option because, honestly, it's cheaper to design and implement. But if you don't specify any safety as part of the project, the safety features may be there, just not activated or used. They're kind of being wasted, all because the hardware just happened to come with safety, but it wasn't the reason why it was purchased or installed. So as a missed opportunity, are you aware if you even have integrated safety on any of your current systems? Or future ones, your new equipment coming in? It may be worth updating specifications when buying new equipment or upgrading old equipment so you don't not only miss the hardware, you select the right hardware, but you're utilizing it to its maximum potential. So now let's look at operational downtime associated with taking advantage of integrated safety with more advanced safety control features. This actually was a side project of our case study on depalletizers, but instead of looking at project cost, we looked at the customer benefit. So in this example, the customer told us that they had around 96 forklift entrances per depalletizer within a 24-hour day. Every entrance leads to a short amount of downtime, only seconds, but multiplied out for the day can really add up. By taking advantage of the features built into having an integrated control system as opposed to the separate safety system upgrade, reset times can easily be lowered, on average from about 15 seconds to about 3 seconds. Over the course of the day, that can save about 20 minutes, which added up over a year can be about 121 hours. The bigger impact here is actually for unplanned stops. These events are less often, but have a much bigger impact on downtime. Depending on where a depalletizer stops in its cycle, can drastically impact how long it takes to restart the machine, ranging from 15 seconds to upwards of 15 minutes. Now, in this case, the customer said these occur about once a week on average, sometimes more. But with integrated safety, we can cut that down to as low as about 1 minute for a worst case scenario. The reasons I'm bringing these solutions up is having impacts is because zoning your safety systems and doing controlled shutdowns is fairly easy in an integrated solution, where it's really cost prohibitive in an independent safety solution. This is one of the many additional benefits you can get by having more control flexibility. Now let's look at troubleshooting time. So I don't know if you've ever thought of it this way before, but safety systems by their very nature are designed to constantly monitor every aspect of the system for any faults or failures that could lead to an unsafe state, always erring on the side of being overly cautious. And when that fault or failure is detected, its whole purpose is to shut the machine down and not let it run again until that problem is fixed. And since your system won't let you run again if there is a safety issue found, figuring out problems quickly can have a big impact on downtime. Now, in the case of operators, they're the first line of defense to troubleshooting any problem, because independent safety systems don't really have much available diagnostic capabilities. It can be harder for them to determine the culprit of something that goes wrong. I mean, think about it. A separate safety system may only have a single system fault light, and that's it. And you got to go figure it out from there. Whereas an integrated safety system has all the diagnostic information built right into it, telling you the status of everything going on. This info can easily be displayed right on an HMI. For example, there's a short between the two wires on interlock 5. Now, if a fault code is displayed in this manner, troubleshooting time by the operator can, in theory, be reduced to 0. And when I say 0 here, I mean the amount of time in identifying the issue. In this case, they know that they need to call in maintenance. They're not going to fix it themselves. But that's opposed to spending maybe 20 minutes just to figure out that they don't know what's wrong and still have to call maintenance anyways. So technical troubleshooting time is meant to represent anything outside the expectations of an operator making a simple fix. In this case, we use times which reflect our Grantek engineers, qualified professionals who already understand the system. So arguably, these numbers could go way up if you have an unqualified staff or people that don't know the system. In addition to more diagnostic information being available in an integrated safety solution, there are just fewer systems to evaluate. We need to connect your computer to one controller as opposed to having to connect it to 2 different ones, one for your safety and one for your machine controls. Overall, these examples are meant to inspire you on different ways that you can look at improving your downtime through integrated safety, which in turn improves your profit as a company. So missed opportunity 5, we've saved the best for last. We start out with technical considerations for individual machines. Now we're going to look at the bigger and the more strategic picture of how companies plan their operational strategy for the future, where everything is connected and digitized, building a smart and safe factory. I'm sure you've heard the phrases connected enterprise or industrial internet of things or industrial revolution 4.0. These are all similar concepts alluding to making improvements in productivity through collecting information from connected devices. At the most basic level, this means that all devices are connected together on your machines and all your machines are connected together, giving you lots of data and visibility into your operations. With this visibility, it gives you better control. The idea of fully connected enterprise goes one step further than just connecting devices and includes connecting your people, your process, your technology, and your knowledge. And all these are used to drive actionable change. And at the bottom here, you can see the typical benefits that are discussed with a connected enterprise: faster time to market for your products, lower total cost of ownership, improved asset utilization, enterprise risk management from a product standpoint, and even workforce efficiency. So ISA published a set of standards known as ISA 95, which describes a hierarchy framework for connecting plant floor operations to enterprise applications. This model helps address questions like which task can be executed by which function and what information must be exchanged between applications. At the lowest level, you have your simple devices on the production floor. This typically refers to the sensors and stuff that collect data. In our case, it would be the safety devices. The level above is where some of the intelligence takes place, the logic and decisions for the process, typically PLCs, in our case, a safety PLC. From there, it is where data collected and integrated all the way up to your ERP system takes place. Once you start to have the data collection and analyzing of the data, you can start to create your dashboards and reports. And chances are you already have some of it, if not most of these pieces already in place. The question becomes, are they optimized and are you taking advantage of them? Now, if you haven't started your Connected Enterprise or MES strategy, I suggest you contact Sam Russum, our Director of Smart Manufacturing. He can guide you through that. But if you're already well into your journey, then most of the infrastructure is there to easily add safety for potentially very little extra. So chances are your company may already have a team assembled for developing or investigating an MES or Connected Enterprise strategy. Some of you may be in your infancy or they may be fairly mature. This roundtable represents a typical task force for developing the strategy. There's just a few examples of the areas of involvement and their respective needs. They include examples of goals, requirements, expectations that each of the groups brings to the table when designing an MES system. The fact that EHS isn't represented is a giant hole, and there's no one to speak up that safety concerns are considered when architecting an MES system. And why is this? Well, generally speaking, it's because neither side, the one being everyone you see here and the other being EHS, they don't really know how safety fits in. So it's just usually not included. When people think MES, they think system integration, workflow optimization, operational data and reporting, not safety. So EHS needs to sit at this table. And so you need to make sure that you can reflect what it is that you need. And that's the missed opportunity. We want to talk about what could you even ask for. So let's look at a couple examples of how safety can fit into your bigger MES or Connected Enterprise strategy. Here's just a list of some of the types of data that are probably already available on your machines. And I want to show you how to take that data and turn it into meaningful information. So let's walk through a couple examples to show you how some of that data can be useful for your organization. All right, now remember, some of these are just going to be examples of what's possible. By no means are these the only things that you can do. My goal here is to inspire you, to show you what could work so you can find what works for your unique organization. The first example will be through emergency stops. Why? Because everyone has them, every machine has them. And so that's just going to be a great starting point. We can extrapolate from there. So example 1 shows a plant with 3 identical production lines, 1, 2, and 3. Each one has a separate group of operators. The data is most likely available today, like I said, on your safety PLC and can produce a report. Now, if you're the safety director, this could be worked into your corporate program for site safety staff. If you are the site safety staff, this might be useful as part of your daily operations meetings. Here's color-coded to help you identify areas of concern. In this case, I picked 5 as the threshold, but you could have picked anything you wanted. In this case, what would you do if you found this? Because clearly some of these are way above what we want. What would you do? Maybe the operators on lines 1 and 3 are not trained properly on how to shut down the machine to clear a jam, as an example. What if we look at that same plant, same line, same emergency stop, but look at shifts as opposed to lines? Let's put an interesting spin on things, doesn't it? Because clearly now you know that shift 3 is the culprit for all the emergency stop buttons being pushed. Now what would you do? Because clearly we've now determined that this is behavioral. If it were spread across every shift, every line, it may be more structural or systemic in the system. So let's expand even further. Say you have 4 different plants across the organization. Now you can show aggregation of data and compare plants to plants. How would this information help you if you were regional safety manager? Now let's combine this example into productivity. Once again, this data already probably exists. It's just a matter of looking at it. So as you remember, emergency stops need to remove power. So in theory, they're going to shut your machine down longer than just a general cycle stop or normal production stop. This is a way of linking it. You can talk to your plant manager, productivity, whoever you need to go, hey, not only do we have safety improvements here, we can improve the downtime just because people are hitting the wrong buttons to stop the machine. Something to consider. Now, if your machines follow protocols like PAC-ML, then your machines or production lines are capable of recording stoppage codes. And if you guys aren't familiar with the primary objective of PAC-ML is to bring a common look and feel and operational consistency. And if you're unaware, this technology is probably already being used on some of your new equipment. What you get is the ability for an operator to select a reason code for why a machine is stopped before restarting. Do you guys know if you're even taking advantage of this capability? I guarantee your engineering teams are familiar with this, but they may not be factoring in safety codes for stoppage, only production. So looking at this example, what would you think if you saw 54% of all stops were jams? Because you know, every time a jam occurs, someone's getting in the machine. So the first example is showing e-stops. Now let's switch gears, tracking something else to look at, let's say, risk assessments, real-time risk assessments. I hope we're all aware that a risk assessment, should be done to determine adequate approach on how to reduce risk, but what if we could do it real time? So this might look like a risk assessment you're familiar with, but unfortunately, a lot of people do them once, they store them in a filing cabinet, and if you're lucky, you look at it maybe biannually. So how do you know if it's accurate? Well, what if we can pull that data? So in this case, we have 10 different access points in this equipment with the data from the risk assessment performed, identifying the number of times it's anticipated people should go into those access points. I've organized them from least frequent to most frequent for ease of understanding. Well, why not use the data from the machine and compare it to that assessment? The numbers here are meant to represent the numbers of times people get into the equipment. On first glance, you might look at this and not know what to think. What if we add thresholds and color code it? And we picked 500% as the worst level. Now all of a sudden things are easier to understand. You can go, ooh, some of these they're getting way more in there than they should. What does that mean to you if you found someone getting in there way more than you predicted? Or what about this little guy? Anyone thinks this looks strange? Zero times? According to our risk assessment, that door should be opened the most for whatever task they have. It should be in the hundreds, if not thousands. What could this possibly represent? Potentially a defeated safeguard. Wouldn't this be great to know? It's probably the scariest one you can get. Now, I purposely chose to have this green because most people don't think of a low number as being bad. Now, if we expand it further, we can do historical averages to see how you compare across the norm. So now you can start to see how they compare. So in this case here, access point 3, they're fairly consistent month to month. That being said, the numbers are super high compared to the expected value. What's that imply? The risk may have just been calculated wrong or people are doing their tasks wrong. But that's totally different than access point 4, where on an average month, it's right. This month was just a fluke. And access point 10, it shows you people do get in there all the time. Someone did defeat it. How would this information be helpful for you? So the two examples I gave are quite different, yet somewhat similar. The similarities lie in the fact that the information is being pulled real time from your operations. It's all there. From your automation systems and being analyzed in completely different ways to drive actionability. Knowing the data is there, what would you like to know? Do any of these hit home with you? Like I said earlier, the possibilities are potentially endless. Figuring out what you want to see can be more challenging than actually collecting the data. A few questions you may want to consider are, what information do you want to know? What information would drive change? What information would help support business cases? So thank you everyone for joining us. That wraps up the presentation. Hopefully you learned a few new things, or more importantly, a few things that you may not have considered before. I'll stay on for a few minutes. If anyone has any questions, please send them in the chat box and we'll get to them. All right, let's see here. All right. First question, if I'm understanding it right, why do a lot of companies go to a zero energy state instead of safe off? Is it that they do not have an understanding of how various safety controls work? If I understand that question correctly, that may be the answer. So this does depend on if you're talking about the lockout tagout, or if you're talking about the protective stop. From a protective stop, and even an emergency stop, safe off is allowed. So that's completely fine. Safe off actually does remove the power, and so it's achieving an emergency stop and a protective stop. It does not qualify for lockout tagout though, which requires a mechanical energy isolating device. So I would have to say the biggest reason there is lack of understanding in knowing how to meet standards like NFPA 79 or B1119, but you absolutely can, for emergency stops and protective stops, use that. All right, another question. With all these technologies and options for safety, how do I know my machine is safe? How would I explain it to OSHA? That is a great question, and one that I wish got asked more. Understanding that with all this new technology can come a lot of additional risks. I mean, I have an entire presentation around answering that question, but I'll do my best to see if I can answer it simply here. So my biggest advice is to leverage industry standards to help answer these questions. In general, ANSI and CSA are written for the employer, helping you understand what you need to do. ANSI B11.0 specifically is the foundational standard in the United States to evaluate equipment, to conduct risk assessments and determine what's dangerous and how you need to guard it. And B11.19 is to tell you how to install safeguarding devices correctly. In Canada, CSA Z432 is essentially combining both of those. But in addition to those two written for the employer, there's hundreds of ISO standards which are written for the machine builders to tell you how to design and program and verify and validate all the engineering stuff. So as an end user, you don't necessarily need to be savvy in them, only to tell your machine builders that they must follow them, hold them accountable. So you could say to OSHA, I know this machine is safe because it follows these standards. I hope that answered the question in a short amount of time. All right, I have one more question. What impact have companies seen with the real-time risk calculator? That's another good question. Unfortunately, I don't have probably the best answer for you on that one. So the real-time risk calculator was an idea I came up with for a few automation conferences I had to speak at, which was designed to inspire people around the future of what smart safety and a smart, safe factory can look like. Because we're on the bleeding edge here. So we've had a few companies call us very interested in trying to pilot a system like that, but as far as I know, no one has actually implemented yet. Remember, that was just one idea of how to take advantage of your safety data. We host discovery workshops specifically to help companies determine what data may be more unique for your organization and useful, and we have done things like that. I just thought that that was the coolest example to inspire people. All right, no other questions. We are right at an hour. Thanks again for joining us.